equation. No matter it's electromagnetic wave, water wave, or any kind of material wave, you always have this kind of expression. Okay, so you want to get familiar with this expression. Well, this could be amplitude of electric field, or amplitude of the magnetic field, or the stress of some material wave. So basically, this is just the amplitude of the wave. Okay, so and this u, it turns out that is a propagation speed of the wave. So this wave equation should be quite familiar to you, and you should sort of remember this. And when we talk about intensity or talk about power, then this quantity is going to be proportional to the square of the amplitude. Okay, however, amplitude in the wave, if you square it, then you end up with a quantity that is proportional to the power, the propagation. And very quickly, we're going to talk about transmission line. In the transmission line, the field quantity, electric field, magnetic field, are replaced by voltage and current. Okay, very similar to a circuit. So the voltage could be a wave, the current could be a wave in the transmission line. Okay, so this is equation that's sort of universal and give you the solutions of this form, or this form, depending on the coordinates you choose. For example, if you choose the spherical coordinate system, then this r is the position of your wave amplitude relative to the origin of the coordinate. OK， 这个 r 呢，就是你看这个波的 amplitude 的位置跟你的原点的距离。OK， and last time I explained to you why we have this expression inside this argument of this function, and then proved to you that with this kind of argument, this amplitude actually propagates in space, right? Now, if you have a cylindrical wave, then this r is the radial position defined in the cylindrical coordinate system. Okay, again, this u comes from this wave equation. Is the speed of the amplitude propagating in space. Okay, well, these two can be simplified to this expression without this radial dependency in the expression. And you notice that well, for the spherical wave, you have 1 over r, capital R dependence. For cylindrical coordinates, you have 1 over square root of r dependence. The reason for this r and this square root of the small r is because that you want to conserve the energy, because I told you that the intensity or power is proportional to the square of this amplitude. So if you square, say if we have a spherical wave and you take a square of it, then it's proportional to 1 over r squared. Okay, but intensity is defined to be power over area. So if you want to conserve power, then you do need to have this kind of dependence. Why? Because if you take an integration over the surface, the whole surface, then you end up with power. For spherical surface, this S, for spherical surface, you know the spherical surface is 2 pi r squared. Okay. For the cylindrical surface, if you have a cylindrical surface, then you have dependence of 2 pi r multiplied with L. Okay, so if you square this, then you end up having a 1 over r squared that will cancel with this r squared in your spherical surface. If you square this, say this is a cylindrical wave, then you take a square of it. This is proportional to 1 over r. And then once you do this surface integration, you cancel this r with this r. Okay. Therefore, the total power is conserved. This is your total power. Okay. So from the power conservation point of view, you need to have 1 over capital R dependence in this wave equation for the spherical wave. And for the cylindrical wave, you need to have 1 over root R dependence in this expression to conserve the total power. Okay. And for this plane wave, basically you just multiply with some arbitrary surface, a plane surface. So you don't need to put this radial dependence into your expression. So when we talk about the spherical wave, we are saying that the wavefront is a sphere. Okay. When we talk about cylindrical wave, we are saying that the wavefront of this cylindrical wave has a cylindrical surface. 所以呢，这个面怎么来的？这个面呢是来自you are watching some amplitude of the wave, so they set the argument to be a constant location. Okay, set it to be constant. Therefore, what did I do? No, it's t. So set a constant time, t equal to constant. Then you have r equal to a constant. And this will give you a spherical surface. Okay, same thing, if you set this to be the argument to be a constant, it means that you're looking into the wave at one particular point. Okay, and then you can construct a cylindrical surface like this. Well, same thing happened to this. This is the simplest. If you set this to be a constant, t minus plus z u to be a constant, and then allow this to be a constant time at some time. For example, you use a camera and then just take a photo of this wave. So you are setting this time to be a constant. Therefore, you end up having z is a constant, and this is a plane surface, all right, at some z location. Any question about this? 这个正负代表是什么？这个正负代表的呢是你的 propagation 的方向 ，right? So take this as one example. Your dr du is going to be minus plus u. No, dr dt. This is the definition of your speed, the propagation speed. OK， 了解了哈。我们还会继续看这个类似的这种还会有继续类似的讨论。So the way we deal with most is the time-harmonic wave. 我们碰到的这个波呢，最多的是 time-harmonic wave， 在我们的这个讨论里头。Because later on you can use a Fourier technique to decompose any arbitrary wave into time-harmonic wave. Okay, so this is the form we're going to see most often in this course. And so we express the amplitude, the solution of the wave into this expression. This is the amplitude of the cosine. And then for plane wave, we put t minus z divided by u into this expression. But at t equal to 0, at position equal to 0, then you could have some arbitrary phase to start with. So usually we'll put this constant phase term in the end. Okay,
just to take into account any starting point for the wave. And with this expression, let's try to understand what a wave is going to describe. Well, any wave has a wavefront. 任何波都有一个波前。什么是波前？ Well, basically, a wavefront is a constant phase plane. OK， 一旦我们用的这个 cosine sin 到里头去之后呢，就有所谓的相位。OK， so we have a phase here, and then if you set this phase to be a constant value, then you can construct the wavefront. So when we talk about a spherical wave, a cylindrical wave, or plane wave, we are saying that the wavefront of those waves are spherical or cylindrical or plane. OK， 所以呢，波前很重要，任何的波都有波前。OK， 那这个概念相当的强烈，也就是说，在这个概念之下，你可以推导出相当的这个重要的一些结果出来。For example, Snell's law, you learn it from the basic physics. OK。 So a wavefront is a constant phase plane. Well, let's try to construct it. Let's try to do it. Well, just pull out the phase of this cosine and set it to be a constant and see what happens. Well, what happens is that if you set this time to be a constant, so you sort of freeze the wave in space. And immediately it gives you a plane that is z equal to a constant. Okay, so we call this a plane wave. So this plane wave, there's a peak, there's trough. And between two peaks, we call it a period in time, or we call it wavelength in space. The whole thing is propagating in space. OK， 所以呢，这里头有波长，有周期。如果在时域上头来讲的话呢，我们说它是周期；如果说在空间上头来讲的话，它就是波长。OK。 And when you set this to a constant, this means that you are seeing the wave at some constant phase point. 譬如说，你把这个设定成say 0 point. Let's set it to be 0. When we put this 0 into this cosine, you get the maximum value. 所以呢，你这里如果设定成0，表示呢，你眼睛在看这一点。 譬如说 ，OK， 最高点。然后呢，你如果继续往下算，这个式子呢，对于这个位置对时间的微分 ，you end up having a speed. So this speed is referred to the moving speed of the point you are looking at. Right？ 这个逻辑了解 ，right？ 你了解这个逻辑？ 这个逻辑的话，是说when you set this to be a zero value, this means that you are looking into this peak point, and whatever you calculated from this setting, then you end up having a speed. This means that you are saying that the speed of this point is propagating with this quantity. OK， 了解吗？所以呢，你等于是在看一个 constant phase point 的这个传输。Okay, what else could you deduce from this expression? Well, you know, cosine function is a periodic function, right? If you have a phi inside, anybody could tell me what is the period of this cosine function? 这个 cosine function 的周期是在相位上头是多少？你当然晓得，对不对 ？cosine phi 它的周期，这个 phi 多少的时候呢，它出现一个周期。Yeah, good, good. 所以呢，一个周期是2派。Good. So let's try to set it. Let's try to calculate. But very fundamental. So let me go through this together with you. Suppose that you have cosine omega t. This is the t minus z over u, constant phase, right? Okay, so we are interested in knowing the periodicity of this wave. So the set, if in the time domain, if I go through one period, let's call it t, this is going to be omega t equal to 2 pi, right? If I try to calculate the periodicity of this wave in time and then label it with capital T. So this means that the omega t is equal to 2 pi. So very quickly you can calculate t equal to 2 pi over omega. But you also know that the inverse of the period is frequency. So this is in fact is the frequency. So immediately you understand what this omega is, right? This omega basically turned out to be 2 pi, 2 pi multiplied with the frequency. So when you write down this, in fact, we don't know yet much about the physical meaning of this omega. But now, the physical meaning of omega is quite clear to you. That is the 2 pi multiplied with the frequency of the wave. OK， 所以从最基本的这个cosine 正弦余弦函数的这个周期性，你是可以推导出这些这个里头的omega u 等等的各式各样的这个它的物理意义出来。OK， 非常简单直接的一个这个计算，但是呢你要自己有这种思考的能力去把它给做出来。OK。Well, so usually we call this angular frequency. Okay, so this is a very quick example to tell you how to sort of solve the to understand the physical meaning of those parameters. Well, same thing. This t in the time domain is the time when this wave propagates from this point to this point. And in the spatial domain, the length between these 2 points is the wavelength, right? So the time, the period of time between these 2 points is going to be equal to the time the wave propagates one wavelength with a speed of up. OK， 这个时间呢，这个波从这里跑到这里的这个时间呢，你实际可以是算出来，把它的波长除以它的速度，你就得到这个时间了 ，right? So this t, in fact, is equal to the wavelength divided by up. So if you just put this in very quickly, you end up having an expression that you know it long time ago. That is, if you multiply frequency and wavelength together, you end up having a phase velocity. Okay, so this can be derived. It's not something you have to memorize, but it's more important for you to understand how to derive it from the very basic principle. Okay. In fact, this is sort of this is a simplified form. We allow the plane wave with a plane to be at some z location. 所以这个面呢是我们定义就是它每个面的位置是在 z 什么地方。但是呢这个面 in fact you can propagate with some angle. All right, with some arbitrary coordinate system. If so, in this expression, you end up having a k dot product with r with some arbitrary r direction. Okay, why is this? Because k dot r is a plane. suppose you have a coordinate system like this, and then you have a plane propagating along this direction. Okay, imagine that this is the XYZ coordinate system, and then you propagate a plane along some arbitrary direction. And if you look at an arbitrary point on this plane, and then label it with R, then you end up having a projection of this R onto the surface normal direction, and then you have a constant length right here. This length is constant. 对一个面来讲 if you project any point on this plane onto the surface normal direction, then you have a constant length. 所以呢 suppose that this is a k direction. All right, it's some arbitrary k multiplied with some unit vector. 所以呢，你这个 project 过来的话是 r k dot r is a constant, and this expression is a plane. 这是你高中的时候学过的几何，对吧？有没有学过？ So a more general form is that you replace this with k dot r. Okay, this is a general form for plane wave. 有没有问题？所以一样，你如果把这个相位拿出来的话，这个我们有个 t minus k dot r plus phi 0 equal to a constant, and set it t equal to some constant value. Then this means that your k dot r is a constant. And then you know k dot r from this geometry. K dot r is a constant, means a plane. Okay. 了解了 right? So this is plane wave. Okay. So for a wave, for electromagnetic wave, you give it different names if you have different wavelengths. I just told you that a wave, especially for time-harmonic wave, you have some wavelength, a well-defined wavelength. For electromagnetic pulse, you don't have a well-defined wavelength, okay? But for time-harmonic wave, you do have a well-defined wavelength. For different wavelengths, you give it a different name. For example, if your wavelength is very big compared to, sort of comparable to the dimension of a house, a few meters, then we call it radial wave. Okay. 不同的波长，我们给它这个波呢不同的称呼。For example, if you have a electromagnetic wave having a wavelength on the order of a small ball, like a tennis ball, then we call it microwave. So think about that. You have a microwave oven in your house, in your home, right? 在你家里头有一个这个微波炉，它里头的电磁波的这个 wavelength is going to be on the order of a small tennis ball. And if you continue to reduce the wavelength for the electromagnetic wave to a dimension comparable to a bacteria, that is a few micron size, or a few tens of micron, then we call this infrared, 红外线. So if you go to beach and then you can tan your skin, 你可以把自己晒黑，这个晒黑是来自太阳的 infrared. The wavelength is about a few micron. And for a very narrow spectrum, you can see that is visible spectrum. The wavelength of the visible spectrum is some micron, between 400 nanometer for the blue light, and then around 700 nanometer for the red light. 从400到这个400到这个700个 nanometer 的地方。We have the visible spectrum, then that is something you can see. Okay, And if you continue to reduce the wavelength of the radiation to about a few angstrom, similar to the lattice constant of a lot of solid materials, then we call this X-ray. And if you further reduce the wavelength to the atomic scale, then we call this gamma ray. So basically, we use the wavelength to give the names to different to electromagnetic radiation. OK， 基本上这个名称都是来自波长不一样。But don't forget that previously you have a expression that is UP equal to frequency multiplied with the wavelength. So when we say a specific wavelength, we also specify a frequency. Okay, so the name, you can also name the electromagnetic wave according to the frequency, because given a wavelength, there's a unique frequency associated with it, because this UP is a constant value. Okay, any question? For example, today, people are very interested in frequency equal to 1 terahertz. Well, this means that if you have a UP, that is speed of light, 3 times 10 to the 8 meter per second. This means that your wavelength is going to be at about 300 micron. So if you look at some article or publications, people are quite interested in terahertz radiation. So this means that your wavelength is roughly around, it's going to be about 300 micron. Okay, so you need to have the ability to do this conversion. Question, comments? 有没有问题？可以 right? Okay, I told you that we're going to deal with harmonic wave. And harmonic wave basically is described by sine and cosine, a sinusoidal expression. And this sinusoidal expression can be converted into complex numbers according to this Euler's formula. Okay, and in a lot of calculations, it's much easier to do complex number calculation instead of real number calculation. So once you convert this into complex numbers from this Euler's formula, then if we just pull out this time harmonic term and then leave the rest into this variable, then we call this a phasor. OK， 在我们计算里头呢，这个 sin cosine 可以用 Euler's formula 变成两个复数相加。OK， 那because this time harmonic term is everywhere, and for time harmonic wave, and sometimes we don't want to deal with it. We just pull it out and then try to look into whatever left from this simplification. And 因为我们在做这个电磁波的时候呢，任何波我们在乎的经常是它的干涉，还有它的相位。所以呢，这个 exponential j omega t sometimes is not so important. Okay, so you can sort of pull out this exponential j omega t from this expression and leave this phase information into this term, and then just calculate this term to give you all the necessary information about this wave. So by doing this, you create this symbol we call it phasor. Okay, it's a complex number leaving out the time harmonic dependence. And you do this quite often for your circuit theory, right? Quite often that you have time harmonic voltage or current in your circuits. 有没有问题？在你们这个电路学里头，应该都有这种做法，来把这个随时变的部分呢，把它拿开，然后剩下的部分就是 phasor。OK， 那这个有什么好处呢？我们来看一下，复习一下一点点的这个 complex analysis. Well, for complex number, you have the real part and imaginary part separated by this imaginary unit. All right, this J is equal to square root of -1. Okay, again, from this Euler's formula, you can convert it into this expression with the amplitude in front and then a phase term right here, exponential g of phi. And so in the complex plane with x-axis to be the real part and the y-axis equal to the imaginary part, actually you can plot this complex number as a vector in this complex plane. 这是你们国中的时候还是高中的时候都学过了 ，right? So this is called in the polar coordinate system. 在极坐标的这个里头呢，the length of this vector is going to be equal to square root of this s squared plus y squared, and this phi is equal to the phase of this complex exponential, and tangent phi is equal to y divided by x. Okay, so this is a complex number. You can express it on a complex plane. Now, let's deal with two complex numbers. One is z1, one is z2, with their corresponding real part and imaginary part equal to x1, y1, and x2, y2. Each of them can be expressed by this polar form. OK， 这极坐标的形式。那你如果要做相乘的动作的话呢，我要看起来还蛮麻烦的 ，right？ 这个 if you want to do z1 z2 multiplication， then you have to expand it into 4 terms. That is x1 plus ga y1. Multiply with x2 ga y2, then you end up have 4 terms. You multiply these two together, and then these two together, and then the cross product term. But if you deal it with polar form, the calculation becomes very simple. You basically just multiply the magnitude of z1 and z2, and then the phase term basically just a summation of it. Okay, so this is the immediately you see the advantage of this complex calculation by using the polar form, by using the phase angle. Well, the same thing if we do a division, then you just divide the magnitude of these two complex numbers, and then on the phase you just do subtraction. 所以加减总是比乘除要容易 ，right？ 你原来要算4项的，在这里呢，你 x1 x2 相乘 y1 y2 相乘，然后呢，你还要乘这个 cross product term， 总共有4项在那个地方。但是呢 ，if you convert it into a polar form, then the calculation become very very simple because it just involve the multiplication or division of real numbers plus some summation and subtraction in the expression. So this is the advantage of converting the sine cosine into phasor, because a phasor is going to give you the magnitude of the complex number multiplied with the complex complex exponential that involve a phase term right here. Okay. 所以呢，这些计算呢，你可以看到用到这个复数的计算的一个好处在于，就是phase summation and subtraction of complex number basically simplify the multiplication and division of sinusoidal functions in the real space. Okay, but don't forget that the whatever measurable is still in the real space, not in the complex space. So somehow you need to have a way to convert this complex number back to the real number, because the real number is the value you actually measure. 你在真实世界里头量到的是什么？不是这些complex number， 还是这些实数的部分。 Okay, so the question is that if I can do calculations in the complex domain and then convert it back to the real world. So before we use this as a mathematical skill, then we need to ask, is it possible to do phasor calculation first and recover real physical values later? 它是一个数学工具，但是呢，我有没有办法呢，在计算的时候，永远都用 phasor 去下去计算，然后呢，之后再把它给这个 convert 回来。所以complex number is not real. It's not a value you can measure in the real world. So in the real world, basically what you measure is the real number. 来，所以我们来看看这个在真实的世界里头呢，你把两个实数加起来，我是不是能够先把这个复数加起来，再取它的实数部分？如果能的话，那我就可以先去算 a 加 b 这个用这个复数，算完再取实数部分。如果说能够相等的话，那我就可以用这个数学工具了。所有的东西都有个道理在那里 ，right？ 所以 let's look into this rule. Well, indeed, in complex analysis, you can do summation of two complex numbers first, and then take real part of it. This is equivalent to the summation of the two real numbers in the real world. OK， 你在这个 circuit theory 里头，电路学里头，大概用了不少这个复数来做运算。你有没有仔细去检查过？其实是有道理在那个地方的。For example, in the real world, you multiply two real numbers, and this is equivalent to that you multiply this complex number with the real number and then take real part of it. Okay, so for this kind of multiplication, you can do it. Okay, because basically this is going to be equivalent to the real world operation. And for differentiation and integration, basically it also allows you to do complex differentiation or integration first, and then take real part of it. This will be equivalent to starting with real number in your calculation. All right, and then take differentiation and integration. 同时呢，如果说在这个复数 complex domain, if A equal to B, then it's equivalent to the real part equal to each other. Okay, so based on those rules, basically it's safe for you to do complex addition, subtraction, integration, differentiation first, and then come back to take the real part of it to give you the real world value. OK， 所以其实你可以看到我在上这个课的时候，其实还蛮严谨的，不是直接把一个数学的式子呢，或一个数学技巧拿来做计算，你要有个检查。OK， to justify the mathematical tool you use. So the answer to this question is yes. As long as you deal with the addition, multiplication, subtraction, and differentiation and integration. But be careful that this multiplication specifies little a, to be a real number. If you deal with complex number multiplication, well, be careful, this is not going to be equal to each other. If a and b are complex numbers, then you multiply them together and take a real part of it. This is not going to be equal to the multiplication of the real part of a and b. 所以当你在做这个乘的时候呢，你要注意两个复数相乘或两个复数相除的时候呢，这个是不能用的。OK， 那 later on, I'm going to tell you how to deal with this kind of situation. But basically, if you just do the multiplication and if you just do the summation and subtraction and generalize to the differentiation and integration, you can use the complex analysis for your calculation. Okay. 没问题。好。 那我们来看一下跟我们的这个Time-harmonic Field 有关的计算应该是怎么样？现在我们大致上都有一个共识，就是你可以用复数来先做运算。那for Time-harmonic Field, we want to take out this exponential j omega t because this is always there. We can sort of come back to deal with this later, but just calculate the phasor. But very often that you involve the differentiation of the field, the wave. Okay, if we go back to the wave equation. Okay, if we go back to the wave equation, you find that you have to deal with the differentiation of the amplitude with respect to time. So if you take out the time dependence, then we need to somehow to put it inside the calculation. 我们说，我们把这个 phasor 抓出来。The way to create phasor is that you have, in general, you have a wave that is a function of time and position, and then you want to convert it into a phasor that is only a function of position and phase, and then you multiply with this exponential j omega t, and you want to deal with this only, okay, because this exponential j omega t is everywhere in your calculation. But somehow, if you just want to keep this term, you have to solve the problem that you do have some calculation that require you to do differentiation of the amplitude with respect to time. Okay, so let's take a look at how to deal with this kind of situation. 来，我们来看看这个微分的话，对这个phasor 来讲的话，会造成什么影响？ Well, suppose that you have an electric field that is expressed by this term. Okay, if you take a real part of this, basically you are saying that this is E0 cosine omega t plus phi. And this differentiation, well, you have differentiation outside, but according to this, this differentiation outside, you can put this operator into this this parenthesis. 你可以把这个微分呢放到这个括弧里头来。So let's do it. Okay, let's put this differentiation into this parenthesis. Then the only thing related to time is this term. So this differentiation is going to give you j omega in this calculation. Okay, and the phasor, basically now your phasor is multiplied with the term that is j omega. 所以呢，这个 operator is replaced by j omega. So if you have any time differentiation, then you basically replace this temporal differentiation with j omega in your calculation. Okay, and then you end up having the factor exponential j omega in this expression. OK， 所以呢，你所有计算里头都会出现这一项。那把这个拿掉，做计算的时候呢，你如果碰到这个对时间的微分的话，那你必须在这上头乘上一个 j omega。这样的话，你所有计算都可以用phasor下去做计算。OK， 然后呢，之后再把这个 exponential j omega 拿进来，重新reconstruct your real expression. Okay, so in the future, if you want to do a phasor calculation, then you convert this differentiation into this form. Okay, and how about integration? If you want to do integration, well, basically you start from this real number. 在这个是真实世界里头的项 right? And then this E is expressed by this real part of this complex number. And then this integration outside this parenthesis can be put into this integration outside this parenthesis can be put into this parenthesis to do the complex integration first. And the only term related to the time is this exponential j omega t. So you end up having the phasor divided by j omega in this expression multiplied with the time harmonic term. 你注意我们做这些动作的最主要目的是什么？就是因为在 time-harmonic field 里头呢，你永远都会出现这一项，所以呢，我们希望我们在计算的时候呢，就把这一项拿掉。但是拿掉的时候呢，你如果碰到这个对时间积分或者是微分的时候呢，你必须把这个积出来结果或者是微分出来结果呢，乘上原来的 phasor。This is the whole purpose. Okay, so with this integration, you end up having 1 over j omega. So in the future, if you deal with this real number integration over time, and you want to calculate it by using phasor, then you have to divide this phasor by j omega. Okay, so this is sort of a process to create the mathematical tool for the calculation later on. Okay, any question? So we'll rest for 10 minutes and come back.